Hello everybody and welcome to the 37th webinar in the RUS series. My name is Georgia Karadimou and in this webinar we will learn how to derive nearshore bathymetry using Sentinel-2 data. I would also like to mention that this exercise is based on a concept developed by Elena Papageorgiou. So let's have a look at the structure of this webinar. We will first have a quick introduction about the RUS service, followed by some recent updates that we have included in the project. We will then have an introduction about the study area. We will continue with some information about Sentinel-2 satellite and its multispectral instrument, and then we will have a bit of theory about bathymetry. Then we will move to the exercise in the RUS virtual machine, and a Q&A session will follow at the end. The webinar will last around 1.5 hours, including the Q&A session, and please be aware that it is being recorded and you will be able to repeat this exercise by yourself later, once it will be uploaded in our YouTube channel and our training website. You can start sending us your questions immediately as soon as you have one, and with my colleagues here we will try to answer to as many of them as possible. This way we will avoid having too many questions accumulated for the Q&A session at the end. In any case, all of your questions will be answered in the relative document that will be uploaded at our training website together with this recording. Okay. Let's talk a bit about the RUS service. RUS stands for Research and User Support for Sentinel Core Products. It is an initiative funded by the European Commission and managed by ESA with the objective to promote the uptake of Copernicus Sentinel data and support research and development activities. The service provides a free and open scalable platform in a powerful computing environment hosting a suite of open-source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. RUS also provides a specialized user help desk to support your remote sensing activities with Sentinel data and a dedicated training program. Let's talk now a bit more in detail about the training program and the updates of the project. From now on, we will be offering our services in, let's say, 2 different categories based on the RUS VM availability to users. The first category includes the RUS training activities. We will continue offering face-to-face trainings in virtual classrooms, our monthly webinars providing support to webinar replay, as well as support to external training organization and operations. The second category is about individual users and R&D projects. For all the training activities, RUS VMs will be provided to the users as following. Each face-to-face training and virtual classroom event will consist of around 20 participants. The type of the VMs will be provided based on the training category, together with the ICT support during and after the session. In the case of extension, the maximum duration will be 1 month. The PDF tutorials will continue to be available to everyone via the RUS portal, and those who will receive a VM for webinar replay will not exceed in duration the 2 weeks. For the external trainings, 30 VMs maximum will be provided per event, and the participants will benefit from the remote support from our ICT team. Moving to the individual users that want to perform any project, the standard RUS VMs provided so far will not be available anymore, but instead the solution of the Docker container image will be offered. It will contain the RUS virtual environment, and our ICT team will provide the necessary support for accessing the Docker, installing the selected RUS tools on your own infrastructure, and enriching the RUS training kits. You can read more information about the Docker at the link provided on the right. In these websites, you can find all the information about the project in our RUS portal here on the left, so I recommend you to check it after the webinar to get familiar with the service and find more about the updates of the project, register and request a service. On the right part of the slide, you can see and visit our training page, where you can find announcements for our upcoming webinars and events, the recorded videos with the Q&A documents, and our e-learning material, which you can use and practice by simply creating an account. As I mentioned in the beginning, we also have a YouTube channel where you can find all the videos of our previous webinars, and you will also find this one in a couple of days. Here I would like to show you a bit the two websites I just mentioned. So if you go to the RUS portal, you can go up here to the login register and you can click on Create My Copernicus SSO account. You just fill in this form and you register. In case you face any difficulties, please contact us to let you know how to proceed. Once you have an account, you can log in, and if you navigate through all these tabs, you can find useful information about the RUS service, the RUS offer, and the library we have, and the community in general. Even without an account, if you go to the RUS library and click on Train with RUS, here you will find all the tutorials we have uploaded so far for all the webinars that have been created from our service. Now let me go to the RUS training website. Here again, you can just sign up and create an account with your email, first name and last name, and sign up. If you don't receive the verification email, please contact us to fix the issue. So once you have an account, you can access our e-learning part that we have, and in there you will find plenty of courses that you can repeat, and at the end of each one there will be a small quiz, so that helps you to practice what you have learned so far. At the end, you will also receive a certificate if you have been successful. Even without an account, you can navigate to the training section we have, and if you go to the upcoming, you will find the list of all the upcoming events we organize as RUS Copernicus. Also, if you go to the past ones, you will find everything we have done so far, and if you go more specifically, for example, to the previous webinar we released, this one about monitoring volcanic emissions with Sentinel-5P, if you click on More Info, you will find all the information of the webinar, together with the uploaded video on YouTube and the Q&A session document. Now let's go back to the presentation to start with the study area.
We will navigate over Greece, and more specifically, we will visit the southern part of the country, the island of Crete. Crete is the largest and most populous of the Greek islands and the fifth largest in Mediterranean. In this exercise, we will focus on the northwest part of Crete, the Gulf of Chania. So, for this exercise, we will be using optical data provided by the Sentinel-2 satellite constellation. Sentinel-2 mission carries a passive sensor, which means it observes an object of the Earth's surface using external energy sources like the sunlight. It is formed by a constellation of two twin satellites, Sentinel-2A and 2B. They are passing at a polar orbit, meaning that they complete full circles around the Earth, passing always from north and south poles, and they are phased at 180 degrees to each other, and the multispectral instrument it carries has 13 bands. The spatial resolution varies based on the spectral band to 10, 20 or 60 meters. At the equator, it has a revisit time of 5 days. As you can see here, the 13 spectral bands are in frequencies of the visible, the near, infrared and short-wave infrared parts of the electromagnetic spectrum. Those that are of pixel size of 10 meters resolution are for band 2, 3, 4 and 8. They are those which we will also use for this exercise. The product types that are available to users are level 1C and level 2A. As we can see here, both of them come in tiles of 100 by 100 square kilometers, and more specifically, level 1C products contain top of atmosphere reflectances, while level 2A contain bottom of atmosphere reflectances. Basically, level 2A derives from level 1C products, and the user can generate it by applying the send-to-code processor on a level 1C product. Here on the two images, you can see on the left how a Sentinel-1C image looks like and how the associated to it level 2A image looks like on the right, which is atmospherically corrected. Okay, let's continue now with some information about bathymetry. The methods we use for bathymetry estimation, we split them in two categories. the empirical bathymetry, which is image-based, and we also have the analytical methods, which are physics-based. For the empirical one, we have the classification with depth invariant indices, and we have the bathymetry by regression using in situ data where the depths are known. For the analytical methods, we have the physics-based bathymetry inversion and the radiative transfer model inversion that we need to use multispectral and hyperspectral data. From those two categories, we will apply an empirical bathymetry method in this exercise, and we will focus on the bathymetry by regression using in situ data with known depths. There are two potential models for this one: the log lineal model by Lysinga and the lineal ration model by Stumpf. In our case, we will use the Stumpf one. Don't worry about the equation you see here, we will explain each parameter of it a bit later. Okay, here we have the processing workflow we will use in order to derive the bathymetry. First, we need to atmospherically correct a Sentinel-2 level 1C product over water, or we need to use a level 2A product which is already atmospherically corrected, which this will be our case. Next, we need to resample all bands into the same spatial resolution and subset the original image, keeping only the region of our interest in order to save processing time and resources. Then we need to mask the land and keep only the aquatic areas, so we have to create a land mask and then apply it to the rest of the bands. Next step is the sun glint correction. Sun glint is a common phenomenon in satellite images, and it refers to the specular reflection of the sun on water surfaces. What happens is that the water-leaving reflectance cannot be observed easily due to the reflection of the direct sunlight on the air-water interface in the direction of the satellite. Sun glint removal is a pre-processing step of multispectral images, which is necessary when the amount of sun glint prevents the visibility of the sea bottom. There are several sun glint removal methods. In this exercise, we will apply the deglind methodology proposed by Hidley et al. 2005 that describes the linear relationships between near-infrared and visible bands using linear regression analysis based on a sample of the image pixels. For the equation below that describes the sun glint correction, we have the following parameters. Ri is the reflectance from visible band I, Bi is the regression slope, Rnir is the near-infrared band value, and the MIN NIR, the minimum near-infrared value of the sample. Don't worry, we will get the values for all these parameters from the analysis we will make. On the right part of the slide now, you can see how the area looks like before and after we have applied the sun glint correction. Next step in this processing flow is the dark object atmospheric correction. This is an empirical atmospheric correction method which assumes that the reflectance from dark objects includes a substantial component of atmospheric scattering and needs to be subtracted. Finally, we will derive the bathymetry data. We will adopt the model developed by Stumpf et al. 2003 based on the principle that each band has a different absorption level over water, and this diversity level theoretically will produce the ratio between bands. This ratio then will generate a simultaneous change when the depth changes. For this exercise, the ratio will be applied for the pair of blue and green bands. In order to define the constants of the equation, we also need a dataset of points with known depths. In this equation, M1 is a tunable constant to scale the ratio to depth, N is a fixed constant for all areas, Rw is the reflectance of water for bands of the ratio, which are blue and green in this case, and M0 is the offset for a depth of 0 meters. Remember that M1 and M0 will derive from the regression analysis we will perform. Last slide of this theory for the exercise is about Sentinel-2 processor. As you can see, we have in gray the pre-processing steps that are needed before using it, and in blue we have the 6 different modules it contains. In green you see some further processing steps that can be applied based on your application. Sentinel-2 is based on the exploitation and validation of the Sentinel-2 mission for mapping, like mapping habitat, bathymetry, and water quality, and for change detection for coral reef health assessment and monitoring. The 2 modules we will use for our exercise are the deglind and the empirical bathymetry. Okay, now let's move to the RUS VM in order to start our exercise. So you click on the link in order to go to your virtual machine, you insert your credentials, the username and the password, and you click login. Okay, and now we have entered our RUS VM. First thing we need is open Firefox and go to Open Access Hub so that we download a Sentinel-2 image that we need for this exercise. So we just click here in Open Hub, and once we are there, we go here and we log in with our account. If you don't have one, you sign up and you create one, and then you can log in. Okay, now that we're logged in, we are moving over Greece, and more specifically, as we mentioned, over the island of Crete, in this part on the Gulf of Haya. Let's just draw a small area to set it, and let's go to insert the parameters. So the date we will use for this exercise will be 24th of August of 2018. So you go here in the sensing period and you go to August 2018 and you select 24, and you do the same for both of them. 2018, August 24, as a start and as an end period, because we want to have the images only of that date. As mentioned, we will use Sentinel-2 data, and we can go here in the product type and select S2 MSI 2A. Then we just click search. And we have 2 results. Let's unzoom a bit. From those 2 images, the one that we want to use is this one, the left one from the 2 that you can see. It has this name over here. So this one, you just click on the download icon to download the product. In case it is offline, a message will appear. You will click OK, will initiate the retrieval, and a bit later it will be available at your cart. Close this window. Okay, and we can start with the exercise.
So now let's go to Shared, and we go to Training, COAS01 Bathymetry Derivation Greece. We double click and we see that we have a folder with some auxiliary data, with the original image we downloaded, and the processing folder where we will store all the outputs. So if I open here the original, I can see the zip product, and I can just go now and double click on Snap to open it and start the exercise.
And here we are. First part, we have this folder opened here, and we open the original. We see here the Sentinel-2 zip file that we have downloaded. So we just drag it and we drop it on the left in the Product Explorer window. And you see that it is reading it. Once this is loaded, you can go to the world view, for example, and zoom in a bit and see the location of the image over the globe. Okay, let's just open this image to see it, so we right click on it and we select Open RGB Image Window. We keep as profile the Sentinel-2 MSI natural colors and we leave the bands as they are. In red we want the band 4, green band 3, blue band 2. We just click OK, and this is creating the image so that we see how it looks like in real colors. Here it is. As mentioned, this area here in the center will be the area that we will focus on. Fine. We can close that and we can go on the left here on this key and expand it and see that the image contains some folders. From these folders, if we click on the bands, we see the 13 spectral bands we mentioned that a multispectral instrument has. From those bands, we need bands 2, 3, 4, and 8. So let's just go and double click in each one of them, band 2, band 3, band 4, and band 8, just to visualize them, to see how they look like. And let's go to Window, Tile Evenly, so that we have all 4 of them. We go in the Navigation tab and we select these 2 parts so that we have all 4 images moving at the same time. Here we are. Here is how they look like. I just wanted you to see this, so we can now close them and we can start running our exercise. Let me close all of them. Great. As we said, we need all these bands to be resampled in one same resolution, and we need the one of 10 meters because this is the resolution that the bands we will use have. What we do, we select the image and we go here to Raster, Geometric Operations, Resampling. We have the product here in the name selected, and here you see at the target product the name. It just adds at the end the resampled, but we don't really need all this long name, so we delete some parts, and at the end what we leave is Sentinel-2 to know which is the mission. We leave the type of the product and we leave the date it was acquired. We click here on Save As and we select the folder that we want to store it. Then in the parameters that we have for the resampling, you select here to define the size of the resampled product by reference band from source product. So what we say is we select that read band 2 and take the size this band has and just resample all the others based on this. So at the end they all have the same. And we click Run. Now for demonstration purposes I will not run it. I have already created for you. So I will just load it. I have it here in the processing. And now we can see that it contains exactly the same 13 bands. It just now has them all resampled in the same pixel size. Pixel resolution, sorry. Okay, once we have done that, we do not need the whole area as we said. We need a small part of it. So we need to create a subset. We do not use anymore now the first original product. We will use now the second one. So we select it and we go to Raster, Subset. We're waiting for this to load, and here on the left you can see in this window the preview. We go to the pixel coordinates and we select the start and end X and Y scenes. In this case, as the start X scene, we will set 4810. Then we go to the start Y scene and we set 4588. Next one, we set it as 0866. And last one, we set it as 7030. Just click on another one and you see that here on the left you have this small blue rectangle showing the area that you will subset. And then you just click OK. Once you have clicked OK, You can see that here on the left, the subset has been created. If you right-click on it and open an RGB image window with these bands, 4, 3, and 2, and you click OK, you will see that simply the area that you have now has been subset, and this is the result that we will work with. Good. Since we will work now from this point and on with this date, with this image, sorry, what you do is you right-click and you go Save Product As. It will give you a message asking you if you really want to convert the product, because it will be converted to BMD matte format. You click Yes. You navigate to the folder that you want and you name it as subset in the beginning, and then you leave the rest name as it is. And you click Save. Once you have done that, you go here on the left. Once it is saved, you right-click on it, you close this product, you go to the processing folder, and you open the subset that you have saved. Great. From now on, we will work with this one. As we mentioned, first thing we have to do, we have to create a land mask so that based on this, we will mask the rest 4 bands we will use, and we will remove the land area from the image. How do we do that? We go on the product, we right-click on it, and we go to Band Maths. Here on the name, we need to name somehow the band, so we name it land_mask. Having done that, we go here down to Edit Expression to tell the software how to create the land mask. Remember that band maths is something that we will use quite a lot today for this exercise. So what do we write? In the expression, we want to mask it, and we will select to create the mask with band 8 because it has the best contrast in reflectances for discriminating land from water. So we go on the left on the data sources and we select band 8. Immediately this appears on the right in band expression. We have band 8, and what we say is if band 8 has values which are more than 0.05, what we do is we call them, so then, as no data values. Else, you just call it 1. So what we will basically do is we will name all the areas with land and with water with 1 or no data value. The expression seems correct, so we see down here it writes OK, no errors. So we go and we click OK. We have this, and then we click OK again. And now if we see, this is the land mask. With white are the areas that we have water, and with black color, with actually no color, we have the land. You can see that also this band has been added in the list of bands over here as land mask. Now that we have done it, what we want to do is we want the 4 bands we will use to be masked out. So we have to do the same step 4 times for each band separately. What do? We just go here, right click, and we go to band maths. And how do we name that? We name it B2 land mask because now we will mask the band 2. And we will go to the edit expression to set the expression. And the expression basically goes, we take band 2 that we want and we multiply it with which one? If we go down here, we multiply it with, where is it? Here, land mask. So we just insert B2 multiplied by land mask. We click OK, we click OK again, and you can see here on the left, it has been also created. And here it is. It contains only the aquatic areas. We repeat the same step for the other bands. So we name it band 3, land mask, edit expression, band 3 multiplied by land mask. Okay. We can see that this has been created as well. We continue. Before land mask, edit expression, before multiplied by land mask. Okay. And last one, we do the same for band 8, just to make sure that we have done it for all of them. Land mask. So we have band 8 multiplied by land mask. Okay, again. Now we have them all. Now that we have them all, what we do is we want to make sure that we will not lose these 5 new bands we have created. So we go on this product, we right click on it, and we select Save Product. And this way we save the bands. Okay, we do not need now anymore these view windows here, so let me just close all of them so that we continue to the next step, which, as we said, is the sun glint correction. This is now one of the important steps. Let me open the band 8 land mask again. And what I will do now is I will import some auxiliary data, some polygons that we have mentioned, because as we said, we need to set a standard area as samples so that it reads some pixels and it's using it to apply it for the rest of the image. I have already created some polygons here, so I will just insert them. So if you go to Vector, Import, and then import Esri shapefile, and you click here, just go up here and navigate to the folder that we want. So we want to go to Shared, Training, and we have the auxiliary data folder. If you open it, you see here the geometry polygon shapefile. You select it and you just click Open. Here you select No, because we don't want the polygons to be as individual masks. And now we have over here these 4 polygons that have been added. Don't worry, they may appear with a different color to you. That's not a problem. Every time that you open them, they appear with a different color. So here they are, these polygons. What do we want to do now? We need the information, the values of the pixels. So we go up here in this icon that says Scatter Plot, and we click on it. What we will do, we have the scatter plot. We will select some information. First of all, here we will choose the Use ROI mask, which is the region of interest. In this one, we go and we select which one we want. We want the geometry polygon. So we click on that because we want to use as input mask whatever is in the pixels that are within these geometry polygons. Having selected that, we need to go here and define the X and the Y axis. For the X one, we have the subset product selected, And we have selected the band 8 band landmask. So as it is over here. And then we go a bit further, and for the y-axis, again, we have from this product, the subset product, but now we want to visualize the band 2 landmask. Remember, we will repeat it 3 times. So first we will have in the x-axis, the horizontal one, band 8, which is the near infrared. This will remain like that, and here on the y one we will do everything once for the band 2, then for the band 3, and finally for the band 4. We will repeat that for all 3 bands because we want to perform the regression analysis. Once we have inserted this information, what we do is we just click refresh. When you click refresh, you get here this information, these values of the pixels. We right click and we go copy data to clipboard. Once you have done that, now you need to put them in an Excel. Here we have already for you, if you go to the applications on the top left, Office, we have the LibreOffice calculator, which is the Excel, basically. So you just open one, you come here, you just right click and you click paste. In this window that appears, you click OK and you see immediately all this information over here. Let me just make them a bit bigger. Okay, now that we have it like that, we are ready, almost ready, to start creating the regression analysis. First thing, if you want to be able to use these cells, what you need to be sure of is just select all cells and go over here to edit and deselect the cell protection. We do not want the cells to be protected, otherwise we cannot use them for anything else we want to do. What we can do is we can select all A and B columns before we start, and then we go to Insert, Chart, we click on that, and here we see these windows appearing. What we need to do? First of all, we need to select as a chart type the XY scatterer, and we select here this one, the points only. Going to the next one, we can skip that and we can go to the data series and we can basically define here the information. So what it says is that the data series it will use is the subset that we have. Correct. The name, okay, let it be this name because it's of set 1. And now we need to set the X and the Y values. As you can see, since we have selected all columns, both of them, it says that the values that it can work with, they start in the X1 from A4 and they finish at A718. If we go here on the left and we check, we see that the first one that we want to use is on A16. So once we have this selected, we just go down here and we say A16. Having done that, you select the Y values, and again here you set, instead of 4, you set 16. So now it contains all the information from the very first value to the last one of both columns. Clicking next, we go to chart elements. You can give it a title, a subtitle, and you can write anything you need on X and Y axis. Let's leave it as it is for now, and let's click finish. Let's just click on the values here and go to line and make them a little bit smaller so that we can see it better. Okay, this way it looks way more clear. Good. We have this one here, but what we want to do is to perform the regression analysis. As we are now here, we just go out of it, and we have columns A and B selected, and we go to Data, Statistics, Regression. And here it is asking you which are the data that it needs to calculate. So for X and Y, we need again to set those that we have the values for. We do not need all of them. As you can see here, it has selected everything. We just need from 16 to 718, as we mentioned before. And again here, the same for the other one. We need from 16 to 718. Perfect. Once this is created, you see here this information. You just select in which one you want the results to be seen. In this case, for example, we can select them. We can write that we want them to be in sheet 1 as it is now. Just please make sure that you keep the exact same naming that the software can understand. $, and let's select, for example, cell column E, cell 1, to have the results. And we click OK. And here we have all our results. As you can see here, all this information with the values and everything. Now that everything is calculated, you right click on them, and what you do is you go to Insert Trend Line over here. You see that the line appears. We can give it a red color so that we can see it, and we can make it a bit wider so that we can better see the trend line. So there it is. Having created the trend line, we right click and we select Insert R-square and Trend Line Equation. Why? Because this is what we need. As we mentioned in the theory, we need these numbers. We need this one, the 0.9157. Once you have created that, just go to File, Save, go to the Shared, Training. You can go again to the Processing, and you can name it, for example, Band 2 Landmask. Landmask. Okay, and you can save it. You go back to Snap, and you repeat the same for bands 3 and 4. So you keep everything as it is. You just go in the y-axis, you go here, band 3 landmask, you refresh, you get new values, right click, copy data to clipboard, you go back to the calculator, and then you insert in there the information and you apply again the regression analysis. Same for bands 4 as well. We can close that now because we have finished with that. Remember that you need to keep the values that come from the regression analysis. And once we have that, we continue now with the band maths. What do we want to do now? Since we have all these values that we need, we go now to perform the deglind. Again, we go to this product we right click and we go to band maths. We name this one as B2 deglind because we want to start to deglind each band separately. And we do the same for band 2, 3, and 4. We name it like that and we go to edit expression. And what do we do now? Now we want to use the band 2 landmask in this one and do what? We want to remove the value that we got from the equation of the regression analysis before, which is 0.91574. You don't need to keep too many digits. And then you need to multiply that with the following. You multiply that with band 8 landmask, remember that we used this one, minus 0.001. Why do we do that? We do that because we said that we need the minimum value of the area, and for band 2, for this band, the minimum one is 0.001. Having created that, we just click OK, OK again, and here it is. You can see the band 2 deglind mask. Again, as we said, we go back and we repeat for bands 3 and 4. Note now that for those we have different numbers than we had for band 2 from the regression analysis. So we go here now and we set for band 3 landmask the value that you get from the equation is 1.00116 multiplied by band 8 again, the band 8 landmask, and then you remove 0.001. OK, OK again, and here it is. Last but not least, we go again to band maths. This time we name that band 4 deglind, and in the edit expression we select band 4 landmask. For this one the value is 1.0223, and we multiply it with band 8 landmask, and again we remove the lowest value, 0.001. Click OK, and the last band is also created. So we have all bands 2, 3 and 4 that have been deglind. Now, if you want, we can right-click on that and create an RGB image window, but not with the originals bands 4, 3 and 2, but with the deglind ones. So if we go a bit lower, we select B4 deglind, B3 deglind, and B2 deglind. Okay, and this is how it looks like. Let's continue now with the one that we said about the dark object atmospheric correction. And as we said, for that one we will use the bands 2 and 3 because these are the two bands, the green and the blue, that we want to use for the ratio afterwards for deriving the bathymetry. First of all, to remove those dark objects and to correct the image, we right click on that, and again once more we go to band maths. We will name the band referring to 2 as B2 DOS, dark object subtraction, and we will go to the edit expression, and in there we will select the band 2 deglind, and here we will remove 0.005. We click OK, and again OK, and this is the band. One last time, we right click, we go to band maths, we name this one as B3 DOS, B3, we edit the expression, we select the B3 deglind, and now we remove from that the 0.001. We click OK and OK again, and here we have it. Okay, let me tell you now why in band 2 we had 0.005 and in band 3 we had 0.001. If you go, for example, in band 3, if you go in the band 3 deglind view and you click here on histogram and you select this ROI mask and the geometry polygon, you get in this histogram the minimum value. In this case it is 0.001. That is why we insert that one. For each band you can create a histogram and get the minimum value that you have. So we'll close that, and since we can have a look here in the bands, we have created quite a few bands. It's better to just right click and save the product to be sure that we will not lose any of what we're working on. Let's just close all these views, we do not need them. And let's move now to the step that we will derive the satellite bathymetry. Last one here is we right click again, we go to band maths and we name this band as the ratio of bands 3 and bands 2 that we said in the theory. We go to edit expression, and in here, if you remember that equation, we now need to insert the parameters. What do we write here? We want the log of 1000 that we said is the n number which is stable for all of them, which is the default one. We want to multiply it with which band? The band 3 DOS. And then we want to continue all these to go to the log of 1000 again, multiplied now by band 2 DOS. Remember that we said we want to use now the green and the blue bands that have been already subtracted the dark objects of them. We see that there are no errors, and now we click OK, and again OK. And this is the band created. What we want now is we want to export these values of the pixels, and how to do so? You go to raster, export, extract pixel values. Okay, in the source path we see this one. In the output directory, I just advise you to go again to the shared, training, and within the folder that we are working, the processing one. And you just select it. Now we need to go to the parameters tab and set here some information. For example, for the coordinates, you click here on the plus icon and you go add measurements from CSV file. And over here we navigate to our folder, and if we go to the auxiliary data, we can see in there the bathy chord txt, and you just select it. You can see here that this information has appeared. Remember, unselect the tie point grids and the masks, these two options, and select the include original input. Finally, just click extract. You see that it is creating the output. You get the message that the pixel extraction tool has run successfully, and it has written the result in the processing folder that we set. We click OK, and we close this one. If we now go to the processing folder, we can see that the PixX product LD map txt has been created, as well one txt with the level 2A measurements. Again, let's go to Applications, Office, let's open the calculator, and in here We go to File, Open. We navigate to the path that we have the results. And from this one, we open the TXT with the measurements. And you just click Open. OK again. And we have all this information over here in all these cells that correspond to the pixel values. As we said, remember to select all the cells and go to Edit Cell Protection. Now, we need to use in the x-axis the information of the pixels of the band that has the ratio of B3 and B2 bands. And if we go in the beginning, on the y-axis, we want to use the depth, which is in meters. So we select Control, and we just select the column B as well. Note here that the information we need starts from row 8. As we did before, we go to Insert, Chart. We select as a chart type the XY scatterer. We continue to the next one. And as X values, we need to insert only from BT, if we go down here, BT8, as we said that it starts, until BT54, and then we go to the y-axis as well, and in the values again we want to use the values from B8 till B54. Okay, now that we have both of them correct, we continue to the next one. If you want to insert anything in here, go on, and then we click Finish. And this is our result. Remember, if you want, you can modify that. You can make it a bit smaller so that you can see it better. And as we did before, we go to Data, Statistics, Regression, and here we set again the information like we did before. Okay. And for that one, we had the BT. We select the results and we want them to be in BV1. Okay. And if we go now to the right, we see here all the results. Going back to the chart that we have over here, right click, insert trend line, let's make it again red, perfect, and having inserted that, right click, insert R-square and trend line equation. And now from this one we get the M1 and the M0 that we need for the next step. If you remember, these are the numbers, minus 37.1 and 41.9. Again, this you can save it if you want. And having taken these numbers, we go back to Snap and we apply the last band math. The last band math, we right click on it, We go to band maths and we name that as BD, satellite bathymetry derivation. In this expression now that we go to edit, we just insert the equation. So the M1 that we said that we need is minus 37.118. Then we multiply that with the band that contains the band ratio of band 3 and band 2, and at the end we add the M0, which is 41.926. Sorry, this point. Okay again, and here it is. It has been created. Now that it has been created, we can go to color manipulation and check out what is happening with the values here. And also we go here in the import color palette, we navigate to our folder again, and in here in the auxiliary data you can find the bathymetry color palette. You click open. Again, as we set values from 0 to 24, and this is how it looks like. Again, let's right click and save the product to make sure that we save all the changes we have applied. And now let's move to the final one that we said, that we want to use the send to Coral modules. We want to use two models. We want to use the deglind, and then we want to use the empirical bathymetry. So this is the final result. If we now have this product selected and we go to optical, thematic water processing, send to Coral, processing modules, and select deglind processor, we have this window. Just leave at the name the deglind that has been added at the end. Make sure that the directory you have set is the processing one. And if you go to the processing parameters, we necessarily now need to the sun glint areas to write the geometry underscore polygon that we have our information. Please make sure that you write it with the exact right characters, capital and non-capital ones, as it is written. And as source bands, we select only bands 2, 3, and 4. Just select them by having pressed the control button. As reference band, we select band 8, and we are ready to run it and have the result. This is very fast, as you can see. Once it is created, it also appears on the left. You click OK. We do not need that anymore. And there it is, with the bands in there. Next, we go again to this resampled one, and we go to optical, thematic water processing, send to Coral, processing modules, empirical bathymetry processor. Over here, we leave the name EMP bathymetry that is added at the end, and in the processing parameters now, as input bands, we select the bands B2 DOS and B3 DOS. Let's find them. They are down here, B2 DOS and B3 DOS. Bathymetry point data. We click on that, we navigate, and we go again in the auxiliary data, and we load the bathy points CSV. This is the one that we want, and we select it. We leave the end value as it is by default, and we run it. This is ready, so we close it, And if we open that and we double click, this is the band that we have. Again, here we can insert the bathymetry color palette like we did before. Open it, set the values from 0 to 24, and this is the final result. If you can see, the one that we had before is this one, the one that we did step by step with all this information, and the other one that we did with the processors of Sentinel-2, it's exactly the same result in our effort to derive the bathymetry. Somewhere here we have completed the exercise. So now let me go back to the presentation and we take it from there.
Before moving to the Q&A session, let me tell you again that you can repeat this exercise by your own if you want to practice, and for that, just go to the RUS portal, register and apply for a virtual machine. During that process, you will need to specify the training code COAS01, and then you will receive the training kit that contains the PDF of the step-by-step guide and the auxiliary data. Also, if you simply want to download the PDF of the tutorial, you can go to the RUS portal and under the RUS library menu, click on Train with RUS, and under the available tabs you will find the COAS01 tutorial uploaded, as well as the rest of our tutorials created so far. Here you see where you can reach us for any questions you may have. I would like to thank you very much for joining, and I will now give you a couple of minutes to pose your questions, and I will be back to you for the Q&A session.
I would like to thank you again once more for joining. I hope you learned something interesting and hope to see you soon in the next events we are organizing. Have a nice day. Bye-bye.